Okay, hello everyone. We're going to start the lecture now. So if you may be quiet now. Okay, so today I'm going to continue about Spark. So this is part 2 about Spark. We are going to deep dive into what makes Spark better than MapReduce and how is that being done. And also we'll look in details with an example, step by step, what does that mean, how things are being executed under the hood in terms for Spark. So let's just continue with where we stopped last lecture for RDD persistence. So persistence is a very important part or important functionality in Spark. So it allows, like we mentioned before, that all the operation, the RDD resides in the memory. And this is part of for intermediate results, it do not get stored on disk, and hence the speed of Spark. So, but for some cases where you need that intermediate result or an RDD that you are going to use again. So there is multiple use for this RDD, and you want to persist it in the memory so that rather than you write it on disk or you repeat the operation, if you are going to call it, you read the original RDD, then perform multiple transformations to reach that intermediate RDD. You persist this RDD in the memory so that you can call it multiple times. So the idea is common in terms of caching. So we all know that what we use caching for the information that we frequently want to use. Rather than reading from slow memory, we cache it in fast memory so that we can do that, we can call this RDD or call this information quickly. So in the essence, but the important bit that you need to be aware of is okay, it's a great functionality, it saves you time. But if you overuse it, that will demolish the need for Spark. Because if you're going to keep large chunks of data, like the RDDs, you keep them in memory and you do not remove them from the memory, then your memory consumption is going to be high. And then when you're running a new transformation, that might be you'll need either to write on the disk or it will delay the jobs, because you need to make your partitions for the data smaller in order to cater that. So in general, definitely it's a useful functionality, but you need to use it where it matters. Because if you overuse it, then you're just consuming memory without very useful outcomes. So persisting your RDDs is for the cases that you know that this RDD is going to be called more than once, so you can perform you persist that RDD in that sense. So in that regard, when you're let's say there is an intermediate result stored in an RDD, you're counting something, you're counting within an error log, you're counting the number of occurrence for the word error. So you're filtering by this word, and you're you preserve that count. And because you're going to use it more than once, rather than you repeat everything to reach this point, okay, because filter is transformation, it's not an action, so it's not going to persist in the memory. So rather than you repeat everything from loading the text file and then filtering and then counting, you persist that count in the memory so that you say, okay, I want to keep this count in the memory because I have other operations on that count. Maybe you're concatenating this count with another count, like error for HDFS or error for something else. Hence, you're going to recall that transformation. So it's better to persist the RDD in the memory. So, and by nature, RDD persist is lazy. So it's not going to be as soon as you call this function, it's going to keep the RDD in the memory. It's going to wait for the action to trigger the execution of your program. And then it will execute the transformation to this point, loading file and the RDD, and then filtering, and then counting, and then it will persist. So it's not gonna trigger all the action as soon as you just say persist rdd.persist. No, it's just gonna rely on the normal flow that all transformations are not gonna be executed until there is a trigger action where it will start with the transformation loading file, filtering, counting, then persisting the count result in the memory. And just like one other thing I wanted also to make you pay attention to is in terms of key value pairs. So Spark is like just like what's it's like with MapReduce. Yep, sorry. Ooh. Thank you. So let's go back to 2 slides. They are there in the slide deck, but just in case. So this is what I talked about in this regard. So persisting and how you can persist. By default, definitely when you want to persist, you persist in the memory. Definitely if there is like not enough memory, then you're gonna persist on disk. Hence, it will lose the advantage of persisting. But nevertheless, as I mentioned, if you overuse persist, then there is not going to be enough space in the memory, and hence it's going to write on disk. So you need to be careful with persist only for the cases that you need it, and then definitely persist in memory since it's faster and hence make your work faster. And in regard to persisting, why persisting in RTD? So you don't recall the whole operation of loading a file, filtering, counting, in order to get this intermediate result. So you just put this RDD, intermediate RDD in the memory, persist it, keep it there so that you can do more transformations. And by nature, it is a lazy operation. So for Spark, it's also just like MapReduce, it relies on key value pairs. So there are key value pairs operations. So group by keys, reduce by keys. All these are operations like currently in the Spark API library. They are already there for you, so it makes your life much easier rather than you build it yourself. Nevertheless, you need to make use of these functionalities according to your need, and always remember that Spark work with the data as in key value pairs. Although in some cases it is more laxed with how it's handling variables, but nevertheless under the hood it is all changing things into key value pairs. So make use of this, because at the end result, if you want your application to be run on a cluster, so you want to achieve let's say good performance utilizing parallel computing, so running on a cluster, then you need to make sure that, okay, you remember that the core concept of map reducing is there. So at the end of the day, you can, for each node in your cluster, they can take part of the key values and then do mapping and reducing under the hood. So even if it is a Spark and it is more lax with variable, yet it's still handling key value pairs, and you have key value pairs operations in RDD as well. Any questions so far? Okay. So in regard now, we took an introduction of how Spark, what's the architecture of Spark, what are the key components, how it's working. But for the Spark programming model, how is it achieving, we said that it is faster than relying on Hadoop MapReduce, it has fault tolerance, and even in terms of fault tolerance, it is more efficient in that regard. It doesn't do replication of nodes. It just go one step back and then re-execute the transformation. So all these are nice features that motivate us to use Spark, but how it's being done under the hood. So this is important for you because like when you're developing your Spark application, you need to maintain these ideas in your mind. Like, okay, how is this happening? What does narrow versus wide transformation means? So there are things that being like acknowledging them and understanding how they are contributing to Spark performance allow you to write better Spark applications and achieve better performance in that regard. So in general, if you want to look at how Spark works, so your application, like create your application, creates RDD, either loading from a file or you're parallelizing some data, as we mentioned before. And then you apply some transformation on this RDD and actions that execute this transformation. So once you like put your application, your code, your application, Spark what it's going to do is going to create what's called a DAG, which is a directed acyclic graph. So in terms of, it's gonna show the roadmap of how things are going to happen in your application. And then Spark is going to look at this graph and determine, okay, how can I stage the tasks within this graph so that I get more efficiency. And according to this, it's gonna distribute these tasks to the node and so that they run in parallel. So like, okay, this is in general like what's happening. Definitely it's like more cryptic, like what does mean it's gonna be creating a DAG? How does that DAG help with the plan and so forth? We'll have a look at what each of these steps mean and how Spark is utilizing that in order to achieve what's trying to achieve. So the first question might come to mind is, what is a DAG? So this is like a very important concept in Spark. So like, as I mentioned, it's a graph. So it's not something like a new technology. So it's a graph. So just like any normal graph, connected nodes with vertices, that's it. But like for this graph, what it is specialized, what's its role in that, and for Spark, is that it is more a specialized graph. It's a directed acyclic graph. So in that sense, what does this mean? Is that this graph, when you transition from one node to another, there is no chance whatsoever that you'll go back to the same node again. So like it's more directed. It's not gonna circle around, so it's acyclic. So the application, you can think about it is in terms of flowchart, but the thing about it is like with flowchart you might have looping, but with a DAG you're more directed. You're going forward in terms of you're transitioning from one node to another in this graph, and then there is no loop back. There is no loops into going back to the same previous node. So this is like roughly what is a DAG, but what does it mean for Apache Spark specifically? So Spark, as we mentioned last lecture, Spark driver identifies what are the tasks. Like when you create your application, Spark driver is going to look at your code and then identify what are the tasks that can be computed in parallel. So what are the things that I can distribute so that the nodes compute in parallel, and how can I partition the data in the RDD? Because as we mentioned, the RDD is residing in memory and it is like subject to partitioning, because you cannot assume that a single RDD is gonna be residing in one machine or like in one node. So the partitions of this data of this RDD is distributed, and hence what are the tasks that are going to be run on parallel on this partition. So using this, like the driver is gonna build a logical graph, so logical flow of the operations. Like, okay, the first operation is gonna be loading the file into the RDD, Then the second operation is going to be mapping, like splitting, like let's say it's a text file, splitting this text file into words. Then I want to do some map to pair. I want to do the pairing, like each word, and pair it with let's say a hard-coded value like 1. So dog 1, car 1, and so forth. So in that sense, it's like, okay, this is my data, and this is what are the transformation I want to achieve on that data. And hence, the driver is going to start building this DAG, this directed acyclic graph. So saying, okay, the first node here is loading the file. Second node here is splitting the file, like the sentences, into words. Third node is map to pair, so pairing this for each word with a hard-coded value, and so forth. Like within here, like the driver is building these nodes and then connecting them so that like it can know what's the transformation, the transitioning from one node to another, and what's happening. And then according to this, Spark would be able to build the execution plan. So it's going to have an idea of, okay, so my execution plan is going to be start from this node, start with loading the file, and then doing this, doing that, and then maybe write it on disk, and then shuffling, and then I reduce, and then put out the output. So this is like the execution plan that Spark is the driver is gonna come up with, so that it knows, okay, this is what I need to do in order to get the results according to the application code that you have submitted. Any questions? We'll look at each of these stages in details. But before we do that, we'll look at it from an example perspective. But before we do that, we need to be familiar with two concepts. That's very important in this regard. So we all know transformations in Spark. So we said last time that there are two operations in Spark, transformation and action. The transformation is an operation that transforms an RDD to another RDD. So it's not a triggering action. It's just transforming one RDD to a new RDD. And as an example, map to pair is all filter is all transformation operations. On the other hand, the action is more like count or write to text and so forth. So within these transformations, we have what we call narrow transformation. What does narrow transformation mean? Is that the operation that's going to happen to transform this RDD to the new RDD do not need the accessing the data partition from different nodes. So as we mentioned, the RDD is going to be partitioned, and the partition is going to the different nodes in the cluster. So a narrow transformation do not need to know what's the data or that partition of the RDD in another node. It's an operation happening on the partition on this single node, on this executor, and then it's going to result the new RDD, which also reside on the same executor. So the parent and the child RDDs do not need to go to another node or to another executor. So here it's if, let's say, we acknowledge that our transformation is going to definitely be faster because there is no transferring between different nodes, and they are residing on the same computer, or the same node, sorry. So then, as an example of another transformation is filter. So the filter transformation is going to do is let's say you have a log file, and you want to filter out for each of the the word error, and it's a log file, and I want to find how many times filter out the word error in this log file. So in that sense, the original RDD is going to be maybe lines of text. And for each line, I'm going to look at, does it have the word error in it or not? Yes or no. And maybe I can create a list. So in that sense, filter do not need to know what other partitions in other nodes have. It's just going to look at the current RDD. OK, it's lines of text. And I'm going to look at, do they have the word error in them? Yes, no. And then result a new RDD. So this can happen on a single executor, on the single node. On the other hand, the wide transformation are the kinds of transformation that requires to get information from other nodes, and hence require like the results from the transformation of other partitions. So in that sense, here it's not going to be contained on a single node. It needs something from other partitions. It needs the results from other partitions, the result of the transformation. And in that sense, like it's going to be relying on different nodes, and hence definitely it's going to be like there is some sharing of the information, whether it's a shared memory or writing on disk. So as an example for wide transformation is like reducing. So any reduce function, in that sense, it's going to rely on, OK, if you map, let's say, in the word count example, or like even in this filter example. So let's say that you have filtered out the word error in this log file, like this part of the log file. And then the next step is that you want to aggregate, know how many times error is mentioned in the whole file. So you want to reduce. So in that sense, you're going to rely on how many errors, like the word error, how many times it's mentioned in this partition, how many times it's mentioned in that partition, how many times it's going to mention in that partition. And hence, you're going to aggregate, reduce the information from multiple nodes in order to say, OK, the word error is mentioned 100 times in the log file. So in that sense, you're going to rely on the result, the transformation happening in other partitions, in order to get the results that you're going to persist or send for the next stage or whatever you want to do. So the wide transformation, it is still transformation, but there is the level of, OK, it dependent on different partitions. It's dependent on the results of transformation from different nodes. And hence, it is a bit more consuming for memory than the narrow transformation. Any question about narrow and wide transformation? Yep. Yeah, so it's just like for the example. So imagine that mapping is a narrow transformation. So with mapping, you don't need to know what other parts of the file which you have distributed, what's the result out of them. Because like internally, you just need to say, OK, car 1, dog 1, whatever. So in that sense, you're just mapping and like fitting to a hard-coded number. So it's only dependent on the partition of the data, the partition of the RDD residing on the same node. So it's the results from the transformation on the same RDD. But for reducing, in order for you to be able to say, OK, how many times error is mentioned, or how many times car is mentioned, or how many times dog is mentioned, and so forth. So what you need to do there is need to be some shuffling between the data from different nodes coming from different partitions in order for you to do say, OK, from partition number 1, car is mentioned 5 times. Partition number 2, 5 is mentioned. The car is mentioned 2 times, so that you can aggregate them. So hence, you are dependent on other partitions, not on the partition that you're working on the single node. And hence, it is wide transformation. Yeah, so it's like here, like definitely the example is map and reduce. So you can think of mapping is the narrow and reducing is the wide. But like for Spark, because it has many other functionalities, so there is filter. Filter is a narrow transformation. Because why? Because it's only filtering the data, the partition of the data in this single node. So I'm only looking for how many times the word error is within this partition of data. So I would say error is mentioned 3 times. Another node is also doing the same. So it's saying how many the word error is mentioned in our partition, and say, okay, 5 times, and so forth. Like for that sense, filter does not need to know what the results or the information in other partitions, just like concerned in its own partition that's working on in the single node. While if you're counting is a wide transformation. So counting is like counting how many times in general within all partitions that the word car is occurring. And hence I need to know how many times in this partition, how many times in that partition, how many times in that partition, and so forth. So like MapReduce definitely is an example, but because Spark is much more rich in terms of the functionalities, so there are other transformations. Like it's not only mapping and reducing. So you need to know what are the narrow and wide transformation, because like this is important when you're developing your application, so that you can say, okay, on this level, all these transformation I consider a single stage, because I'm not yet passing the data to other nodes. I'm not persisting data on memory and so forth. So in that sense, which is narrow transformation is much faster. Because when you're talking wide transformation, when you're dependent on others, you're waiting for the data to come from others, it is slower. So you need to measure, okay, at what level do I need a wide transformation, and at what level do I need a narrow transformation? Any other question? It will become even more clear with the example coming next, because then you'll understand what does that mean in terms of stages and what is a stage in the first place. So the good old word count example come to help. So this is like the code for the word count. So you say, okay, it's the same code. So first we are reading the data from the text file. I'm creating a new RDD for string and integer for like the word count. So the text file, I want first to flat map it. So I want to create a flat map, and then I split for these words according to the space, and I iterate through each one of them. And for each one of these words, I create a key value pair. So dog 1, car 1, door 1, and so forth. And then I reduce by key. So I'm going to reduce according to the key of these. So how many times dog is mentioned, 1, 2, 3, 4, 5. And then I write the file on disk. So this is like the word count example that we all know. So let's look at what's happening in terms of the RDD, in terms of what's being written and what's being shared. So the first line here for reading the file, so I'm just creating a string RDD, so it's a single RDD. So for the second transformation, so I'm here creating a flat map. So I'm applying the flat map operation transformation on my text file. So here I'm getting a list of strings. So here all the word dog, 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 air, door, cat, whatever. So they are all in array of string. And it is still like each one is standalone. So here they're creating the text file, like the RDD from text file, it is a narrow transformation. Flat mapping, because it's going to look at each partition also narrow transformation. Mapping, which is map to pair. So I'm creating the hard-coded pair, door1, dog1, cat1, and so forth. So it's also a narrow transformation. So here it's all on the level of narrow transformations. But when I reach the level of reduce by key, hence I need to get information from different partitions. So I need to know, like, okay, sorry, for the word car, how many times it's mentioned. So I need to get the information from more than one partition. And hence, it is a wide transformation. Because here I'm getting the data from multiple partitions, and in order to be able to reduce them and get the results, which is like, okay, collect the data and provide, like, right in the text file, which is the word and how many times it occurs, and so forth. So this is like roughly what it is in terms of why is like what's a narrow transformation and what's a wide transformation, mapping that to our good old word count example. Any questions? So does this make things clearer? So here, as we can see, so for each partition, like the transformation is occurring on that partition. So when I'm doing a flat map, I'm doing applying the flat map transformation on this partition, and I'm getting a new partition here. And this RDD here, and I'm getting a new RDD here, like the partition of the RDD. So in that sense, I do not need to know what's the result coming from here or from the others. I'm just like, I apply this transformation on that partition of the RDD, and I'm getting a new partition of RDD. So I don't care what others have, like what's the results coming from other transformation. So it's applied on that partition level, and the data can, so here like they can be all residing, like the top ones, they can all reside on a single node. So it's a single node that I can do this, rather than like knowing that there is no shuffling of data. There is no shuffling of information from one node to another, so that they know what's the result coming here, and I can plug it in and so forth. While when it comes to the reduce by key, no, reduce needs to know, okay, from this partition, how many times the word cat is mentioned. So say, okay, cat is mentioned 10 times, or like one from this partition, 2 from that partition, 3 from that partition. So it can accumulate them and say, okay, then the result is going to be cat 10, dog 5, car 6. So it needs the information coming from other partition, because otherwise it cannot aggregate them. Yep. Yep. Mm-hmm. What do you mean AM? Oh, okay. Yep. So here, in that sense, the A is you're trying to add for each of the for the tuples that you have. Like, okay, car 1. You're gonna have a list of car 1, car 1, car 1, car 1, and then you need to add the ones in order to get the results. So in that sense, A is the information coming from another tuple, and you're just accumulating 1 plus 1 plus 1 plus 1. So you need 2 values in order to do that. So you can accumulate them and get, okay, this is from the first tuple, second tuple, third tuple, fourth tuple, and so forth. Any other question? So, okay, so now with this example, hopefully the narrow and wide transformation is clear. But why does this matter? Like, why do we need to know why, like, narrow and wide transformation? Oh, so at the end of the day, I'm gonna just write the code and that's it. Well, it matters because it affects the execution plan. It affects how the directed acyclic graph is created and how Spark is going to execute your like operation, the transformation and action, and get the like optimized performance. We'll look at how this happening in that sense. So what Spark is going to look at in terms of the narrow transformation that can only need to happen on a single like node, or like they don't need to pass information from or materializing the data in the memory. I can say, okay, all these are considered in one stage. So like in our example, reading from text file, flap map, and map to pair are all in the same stage. So this is stage one of the execution. So hence I can say stage one of the execution can happen on node this. So the plan, the execution plan that the DAG scheduler is going to do is going to look at, okay, what's the lineage between this transformation, and hence, okay, this is like, okay, this is the lineage, so this transformation, this RDD is transformed according to this transformation and getting this new RDD and so forth. So it's going to look at all these transformations and say, okay, so this is the directed acyclic graph of your operations. Like this is what's happening in your application. And according to this, okay, so I can say this is stage one, and I can like map stage one. Like I can say that stage one can be executed by these nodes, and then stage two, which is the transformation that require information from other partitions. So it's the wide transformation. This is stage two, and it's going to be happening on these nodes because it's going to be passing information from one node to another, and hence I can apply these and then get results. So for the execution plan, which is very important for how Spark is doing things, it can delegate resources and can determine, okay, in this operation, like this is the whole, all these transformations, all these parts of the operations are going to reside on single node, then we're moving to another node, and hence and so forth. So when Spark DAG scheduler is trying to put on execution plan, it's important for it to know where is this like partition where we transform from okay single node operations to okay operations that require results from different nodes. So this boundary, when a shuffling is happen, is very important because it can determine the stages of the execution, and hence the allocation of resources. Okay, say, okay, how many resources do we need? How many RAM do I need on this transformation? Is it more? Is it less? And hence Spark can maintain this level of good utilization of resources rather than just pushing everything randomly. So this is, the execution plan is important so that Spark can utilize the resources properly, and without this execution plan, without knowing where do we transfer from one node to another, it is not going to be useful for Spark, because like if I don't know where the stage one ends and stage two start, then what's the point from planning in the first place? Any question about the execution plan? So here, like, okay, once you know that from these stages, I have these stages, then I can go forward and put in action in terms of determining the task that I can distribute. Pay attention, like here in our example, it might be like trivial in terms of like I have 2 stages. So it might be like, okay, yeah, that's not too bad. But for some applications which they have like multiple stages, that's very important because some stages are more resource consuming than others. Like some stages have more transformation, have less transformation, have persistence. Like also here, pay attention to something is what we mentioned in regard persistence and memory. So if you persist, if you force persistence, if you say, okay, persist this RDD in memory, then what you're doing is actually you're creating a new boundary. So let's say here in this example, if let's say after the flat map, you determine that the result of the flat map is something I need to reuse multiple times. Maybe you have two modules, that's one reading that flat map and one is doing other transformation, like one filtering and one map to pair or something like that. So you have two transformation. So you determine that, okay, I want to persist the RDD resulting from the flat map in the memory. So if you do that, what's happening here is you're going to create a new stage. So it's going to be stage 1, text file, flat map, then stage 1 finish, stage 2 mapping or something else that you're adding, maybe filtering or something. So mapping and filtering, stage 2, and then stage 3 is going to be reduced by key, collecting, and so forth. So once you determine that I want this data to persist in memory, so you're actually creating the boundary. Even if there is like there is no shuffling between different nodes or between partitions, but you're telling Spark that, okay, hold that RDD in memory. So once you're doing that, you also have the possibility that other partitions or like other nodes look at that memory and do operations, but at the same time, the data, the RDD is persisting in memory, and hence you are creating a new stage. So that's why, like I said, don't overuse persistence, only if you are determining that, okay, persisting this data in memory is going to help the overall performance rather than degrade it. Because like here, when you are saying, okay, it's a new stage, then it's gonna be more like overusing the resources. You're holding that memory, and hence it can, if you overuse it, you can degrade the whole performance. So when we look at it from our perspective, which is, okay, now only 2 stages. So read from the HDFS file, apply the map and the flat map and the map to pair, and then shuffling all this in stage 1. So all this can happen on a single node. On the other side, when you're looking at, okay, read the shuffle data. So I'm going to read the output from the results from multiple partitions and do the reducing, the final reduce, and then write the results to disk. This is stage 2 of the execution plan. So the execution plan is important when we're talking about segregating the like the tasks to the nodes, because like now you can determine within this stage I can have these nodes perform this task. So I split like the tasks according to these stages, and I distribute it to these slave nodes. And hence, like for each of these tasks, I know that, okay, this is going to be serializing of data, going here, being stored, doing the transformation, and then if it needs serializing again, going to another node, then I can cater for this. Okay, do I need more network capabilities, more network traffic capabilities, and so forth. So in that sense, looking at what are your tasks, what are the stages that you need to delegate, the Spark here can determine what is the best optimized plan to follow. So all this, like, you need to be aware of it, because it's important that in terms of okay, if you are over persisting data, or if you are having multiple reducing functionality, so you have more than wide transformation internally, you need to know, okay, why is this less, like it is slower than if I have the same thing with other transformation functionality. So this helps you with, at some point, better designing your application so that you do not overuse wide transformation. Okay, always think about it in terms of, this is going to create a new stage and hence persist in memory. So do I need to do this, or can I shift all these? Because as much as possible, if you keep the transformations, the narrow transformation within the single machine, that's better. So minimizing how many times that the data is dependent on other partitions is good for the performance. But like internally, Spark is gonna deal with that. You're not gonna say, okay, how this task is gonna be, like how these stages are gonna be distributed between tasks, or what is the memory resources, the resource allocation internally that's gonna happen. All this is gonna be like, once you configure, like let's say if you're using Yarn, so Yarn is gonna be doing all this for you rather than you are going to be forced to do it. But you need to be aware of it when developing your software, because it's the transformation that you use in the application are gonna be affecting how the resources are being managed behind the scene. Any questions? Okay, so let's take a 5-minute break and then we continue with the internals of Spark.
That if I set this text file and the flat map as the stage 1, and I set the stage 2, for example, to save as text.
Yeah, so what's happening, like you can force this to be added as a stage if you do like persist in memory. So if you determine that the result of the flat map need to be cached in the memory, so you force it, and like what we mentioned in the beginning of the lecture with persist, so RDD persist, so it's gonna be, okay, you have forced Spark to keep this in memory, so you are gonna create a new stage. So after that, but you don't have to do it if it means nothing. But if, let's say, there is another transformation, like here you have mapping and there is another transformation like filter. So mapping require all the data from the flat map, like map to pair, and the filter also requires all the data from the flat map. So there are two transformations require the data from the flat map. So rather than here, then it makes sense to persist because you are going to use it twice. So rather than redoing this, you can just persist this data and do it.
Mm-hmm. So in the boundary, you have the shuffle.
Yes, not necessarily shuffle. Here, because you have forced it, so there is no shuffling.
Okay.
So what you have done with the persist, because like here, like flat map and map, they are both narrow transformations. So there is no shuffling. But what you have done artificially is that you told it, store it in memory. So here, there is not going to be shuffling, but you have told the node to keep it in memory. So you're going to create this boundary. This boundary, what it means in this sense, is that you are going to have the stage that you can, because like the data is in memory, so you can delegate this stage to different nodes. So this is what the boundary is going to mean in this case. There is no shuffling. Like, because flat map or map, they don't shuffle. Reducing do shuffling. Yeah. So, but here, because the data is gonna reside in memory, so it's gonna be there. So you can, like here, you can consider it as the same effect as shuffling, because here what's happening is that for shuffling, you need the data to read it from the memory. So you're gonna read it from somewhere. So you're gonna read it from the memory, from this node, from this node, from this node, because here, you're gonna read it from multiple times. It's not the same machine. So when you're persisting data, it's also, you can do the same thing, because like here, the data is in the memory, residing in the memory. Yeah. Yes, definitely. Here, because like the whole purpose of why you should persist is that, let's say if you have here two transformations. One is map, which is going to operate on this, and the other one is filter, let's say, as an example. So mapping is going to create these key value pairs, and filter is going to, like at the same time, you just want to say how many, or like, how many times the specific word, how many times the word cat is mentioned. So you don't care about the others. It's like a segregated outcome, is that I just want to know how many times cat, specifically cat, is mentioned. So you want to filter everything out, only cat, and so forth. So here, like, you're applying two transformation on flat map. If you do not persist, what's going to happen is, like, for this new action, like what you want at the end result is going to be only the number of times cat is mentioned. It's going to be redoing this. So you are going to reread from file, flat map, and then determine cat is mentioned 1,000 times. Yeah. Yes. So if you have such case that you are doing two things simultaneously, so rather than you repeating this, you can just say, keep this result in the memory, because I know that I'm gonna use it again. So in that sense, it's gonna be better performance. But if you just persist with no reason, so it's like you're just creating here a boundary, you're writing it to the memory for no reason, you're just like adding more like burdening the performance, like how the memory consumption is being done, and just keeping things in memory, that's useless. So if there is a use case, like here there are two simultaneous transformations happening, then yes, you can do it persisting. But otherwise, if you just persist here and you keep flat map results, and then this is like it's gonna be written in memory, anyone can read it from memory for that purpose. So if it is a reducing or other things, it can do that. It's going to be in memory. You have told it to materialize in memory. So that's why it is the same effect here, because when you're reducing, you're reading from memory. So that's why I said you are going to create the boundary, because here you're forcing it to be in memory, and I'm doing something with you. Sorry?
Each stage use different RDD.
Yeah, so for each transformation, it's going to produce a new RDD. So here there is this new RDD partitioned into 4 partitions. You apply flat map, it's going to be a new RDD partitioned to 4 partitions. You apply map to pair, you're going to have a new RDD partitioned into 4 partitions. All this can happen on a single, like one layer, sorry. Or every layer can happen on a single node. So that's why like this is stage 1. But when we're talking reducing, so you're gonna need for the results from different partitions, I need to know how many times cat is mentioned here, on here, and here, and here. So at that time, I need to read from the memory of this machine, and this machine, this machine, this machine. Yeah, so you can have it like Spark is going to do it like this. It's going to split this into different tasks. They can run on the same machine sequentially. There is no restriction that they shouldn't run on the same machine. But they can run on a different machine, same. There is not going to be Like here, what single stage is going to keep it on the same machine. Because from performance perspective, definitely I don't need to write in the memory if they are on the same machine, if I'm applying this on the same machine. But if it is single stage, on this boundary is going to be written in the memory. So another node can take it, same node can take it. It's according to your policy from the resource utilization. So if let's say, okay, you have determined that this task, like for these tasks, Yarn is determined that 2 GB memory is required and this is available on these machines, I'm going to use it and so forth.
So this task, full task, the same thing that assigned.
No, not the same thing. Like they are doing the same transformation, yes, but not the same thing, not working on the same partition, yes. But like they can be on different machines.
Yes. The driver.
No, the driver is going to assign them. So these are on slave nodes, so executors, yes. So for each task, they can go to different executor. Fine. Different. No, the action is the triggering for all the transformation. Here, the task is going to go to the executor. So, yeah. So here, like, this is the driver. So the cluster manager is gonna distribute. So the cluster manager here is the DAG scheduler. So it's going to look at what's my plan, what's my execution plan, and it's gonna apply it. So it's gonna distribute these tasks to the different worker with the Spark executor. And each executor is gonna execute one task.
Every worker has more than one executor.
It can have more than one executor, yes. But every executor is doing one task at a time. It can run another executor after that, yes, sure, but at a time is doing this.
Sorry, once again, one worker can have more than one executor.
Yes,
And one executor can only do one thing.
at a time.
So in this case, one is worker, it can have the different.
It can have different executor because like this is you can consider a machine.
Okay.
Yeah. So this is a machine, and this is a different machine. They have executors internally. They can.
And these execution plans happen in one machine.
So here you can consider. So this can happen on one machine.
Okay.
So text file loading on the RDD, flat mapping on that partition of the RDD, mapping on that partition on the RDD. So this can happen on a single machine. It's more like from the performance perspective, that's preferred. It can like be also another executor on the same machine running a different thing. Depends on the resources available. So if this worker, like it's a server with 16 gigabytes of RAM, then it can do two at the same time. But there is no obligation. It's not like it should, no. Because like each one of those can run separately on a different machine and different machine.
So in this execution plan, we can split them into 4 different tasks.
Yes.
4 different machines.
So here like this is one task. This is a second task. This is a third task.
Each task will finish in.
Yes, so exactly. So here it's like the task is finished. Let's initiate a new task where we take the results from this. Like here, there is the data on this boundary is going to be written in memory. So then the new task is going to be read this part from the memory and then do this and do that. In the memory, yeah, because here it's like it's gonna be on the same machine, so there is no need, like you can apply the transformation, you don't need to persist it in memory. Yeah, so here like let's say the collect is the action, so this is the triggering action. Yep, reduce by key is the wide transformation, it's not the action. Collect is the action. Yeah. The Y transformation, it's a transformation. It's gonna get the information. But after that, there could be another transformation. So there'll be reduce by key, then do something else, then do something else. But the collect is the final action. This is give me the results, give me the array of keys and how many times they, words and how many times they are mentioned. So here the collect is an action, the triggering action. Yeah, so collect is an action.
Okay, but reduce is
Yes.
different.
The final reduce, it can be like if you have a final reduce, but here reduce by key, it could be just a transformation. So after that, you can have other transformations. No worries. What do I have? Okay, we're going to resume the lecture now. So just to iterate, to make things more clear in this regard, so for this execution plan, like for each, like here, for each part, this is a whole RDD. Each part of this is a partition, so we have partitioned the RDD because we want to do parallel processing. So these are partitions of the RDD. And for each of these partitions, I'm running, let's say here, flat map. So I'm running a narrow transformation on this partition of the RDD, which will result another, like a new RDD, which has also partitions. And like for each one of these partitions, I can run another transformation, which is your map to pair. And it's going to be a new RDD, which is also partitioned, and so forth. So this partition, like the new partition and the new partition, you can consider these top three. They can be within a single task running on a single node on the machine, a single worker. So here, this is a single task that's doing this, like the text file, loading text file into an RDD, flat map, and then map to pair on for the single partition. So this is going to be the parent partition, the sibling partition. They are all residing on a single machine. They don't need to be written in memory. So I don't need to persist these partitions because like they are on the same machine, the same node. So here I'm just gonna run the transformation there. But when it comes to reduce by key, because this transformation require information coming from more than one partition of the RDD. So I need to know dog is mentioned 3 times here, 5 times here, 2 times here. So I need to get the information from more than one partition, and hence I need that data to reside in memory so that I can read it. Because potentially here is going to be possible to run it on a different executor. And hence I need to know, okay, so dog is 3 times, 5 times, 7 times, 8 times, and I'm going to read from all of them. So they need to be in the memory in order for me to read it, and hence the need for a new stage. So once there is this boundary that, okay, I need to read from memory, then it's going to be like stage 1, doing this, writing on memory. Stage 2, reading from the memory in order to do this. So you can see here the stage 1 is like reading from HDFS, apply the map, apply the partial reduce, and write the shuffle data. So it's going to write it in the memory. So I'm going to persist it. And then stage 2, read this data that's persisted in memory, and do the final reduce, and then provide the output as the result for the driver. So if the data from the transformation requires to be persisted in memory, then this marks the a stage. That's why I said if you force persist, if let's say this is like a hypothetical example, that in addition to map, there is at the same time a filter operation, filter transformation running. So for the flat map, for the result of the flat map, I want to do map to pair. So I want to do the cat1, do this. And then I want to filter out some words. I want to know if the word error is there, if the word this is there. So I want to do filtering that's happening on the flat map transformation. So I'm running it at the same time, and hence it makes sense to persist this in memory. I can say cache that RDD in memory. So if I do persist, I force persisted, then stage 1 is end here. It's going to be ending here on when I said flat map, then persist. It's going to say, okay, the memory is, the RDD is in the memory. You can do whatever you want. And I can do here is going to be stage 2, which is going to read map to pair, and at the same time this other operation, other transformation, which is filtering, also doing on the same data, the same RDD. So if there is a use case, definitely you can value if persisting in memory is going to be useful. Otherwise, there is no point. If like, it's not going to be add persist stage here if there is no need, if there is no other transformation reading the same. So this is the data required twice for map and for filter. And hence, there is no need for you to create a new stage or like add a new boundary here for the memory. So the boundary is when the data is written. So when the data is written, this is like setting the boundary. Like, okay, I've done all this transformation, the data is written. Second stage is reading from this data and doing this and that, and then maybe write it again. And then third stage, reading from this data and then doing other reducing, and then collection of data and results and so forth. So you can force a new boundary if you do persist, but definitely if there is a need, it's not like I just want to do it for the sake of doing it. Yep. Yeah, so like each partition is going to be the transformation, or like the transformation is going to be applied by a single executor. So the task is going to be done by a single executor. A node, which is like, let's say here, let's say the node is a computer, a machine. The node itself can have multiple executors. But like each executor can do one task at a time, definitely. Like after it releases the job, it can take another task. There is no problem. But at a single point of time, it can only execute one task. So within a machine, it can have multiple executors depending on the resources. Let's say if it's a powerful machine, 16 or 32 gigabits of RAM, 8 cores, blah, 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 then it can have multiple executors and they can run parallel. There is no obligation that more than one task run on the same machine. Spark, the Yarn, or like here, the cluster manager or Yarn, if you're using Yarn, is going to determine should these two tasks run on the same machine or not. But nevertheless, there is no obligation that it should be or it shouldn't be. But like roughly, this can run on the same machine. And like even like for you, if you're working on a single node cluster, so you have for testing purposes, you're working with a single node cluster. But still you said, I want 4 partitions. You can do that. There is no problem with this. For testing purposes, it's a single node, so it's a single machine, and you're running all these 4 tasks on that. You can do it for testing purposes. Definitely in real life scenario, it doesn't make any sense Because if it is a single node cluster, then why you do the partitioning in the first place? But for testing, if like you're developing something and you want to see how it's being done, then you can say, okay, do 4 partition, 4 tasks, 4 executors, and so forth. Any other question? Okay, so in terms like we iterate again in this regard. So all these operations, like even like now you see shuffling, we've seen shuffling, but that doesn't make it an action. So reduce by key is a wide transformation. So it's reading from memory, but it is not an action. It is still a transformation. It's transforming an RDD to a new RDD. So all these operations like read text file to RDD, flat map, map to pair, reduce by key, they are all transformations. But the count or collect is the triggering action. So once, like when the driver reach this point, it's gonna read, okay, count and save the result here. It's gonna start with the execution of the transformation, like starting with the triggering these transformation. By default, it's not gonna do that. Like let's say here, let's draw the resemblance with MapReduce and Hadoop. What Hadoop is doing, because there is no DAG, there is no execution plan in Hadoop MapReduce. So what Hadoop MapReduce is going to do is like, okay, start the application. Oh, there is a mapping function. Start the mapping function. And there is another mapping or reduce function. Do the reduce function. Then another mapping, do another mapping, and so forth. So what is gonna, like what Hadoop MapReduce do is like sequentially going and executing each stage. So each job mapping, they do the mapping. Then the results go to reducing, do the reducing, then do this. So it's a step by step. It's gonna execute without any plan. There is no planning in Hadoop MapReduce. So there is no DAG, there is no scheduling, there is no stages. With Spark, it's a different story. That's why it's faster. So what it's going to do is like, okay, the driver is going to throw the whole application and then create this execution plan according to the transformation and then decide where is the task for each of the task is going in each of the nodes. And then once the triggering action, collect or count, is going to start the execution. They start the transformation. So Spark have planning, which make it more efficient in terms of utilization of resources. Any questions so far? Okay, so let's go into like with our good old word count example, we look at it in more details. So let's say about in regard to the activity that you have done on Thursday. So with the example, first, definitely the first thing that you need to do is like call, like linking to Apache Spark packages so that you import the needed functionalities. So here, like you say, okay, import Spark context, RDD, Java RDD, and Spark conf. What we mentioned in regard to Spark context is important within this configuration. So Spark configuration is key in that regard because it's not going to create your context for you. So once, like here, you imported the required libraries, you say you need to initialize Spark. So here you are going to create the context. So this is the object that determines like, okay, how Spark cluster is going to manage your application. So in that regard, if you say, okay, you need to specify the configuration and you determine what's the name of my application. So just like for the purpose of this example, it's word count. And then you need to set a master, so determine what is the mode, the master-slave mode that you're gonna utilize. So if it is master, so you say, okay, here I'm gonna run a standalone like deployment of Spark. If it is local, then you're determining there is no cluster, it's more local for you. If it is Yarn, then you're gonna utilize Yarn as your cluster management service, and so forth. So in that regard, you need to specify this in your configuration so that once you're creating your Spark context, Spark knows how the application is going to run. Is it going to be run standalone? Is it utilizing Yarn? Is it utilizing Mesos or other things? So in regard to set master, so within the set master parameter that you're gonna set, you can, like by default, it is set to local. So in that set, if you determine local, then you are gonna run with only one worker, one thread. There is no parallel execution. So I'm just like, this is for testing purposes. I want to run it locally. I want to run Spark locally. If you determine like on a single thread, if you say local and then determine how many workers I want to create, so you say local and then between two square brackets, 3. So this is also like in terms of on a single machine, it doesn't matter much how many workers you're creating, but this is like for testing purposes. If you want to see how your application is going to run if you have multiple workers and so forth. On the other hand, if you created your own cluster, so you created your standalone cluster, then you need to provide the URL for this cluster. So if it is Spark on this host and so forth on the specific port. If you're using Mesos, so you're using Mesos for a cluster management, so you need to provide also the URL for Mesos. If you're using Yarn, then the configuration file in Yarn, what we talked about in Hadoop configuration, you need to specify that and also in Spark home folder so that it knows that you're gonna utilize Yarn. And then definitely you need to install Yarn services and HDFS and so forth. So like within when you're setting your, like when you're using the set master parameter, you need to specify how Spark is going to be run in the environment, because otherwise it's like by default it's gonna take local, but nevertheless if you are using Mesos you need to specify that, because don't assume that it's gonna know just if you're you have installed Mesos and so forth. So like an example here, when in your source code, you need to specify this, like here in your Java source code. So Spark conf, set the app name this, and the master is local. And when you're submitting, so this is like here, it's different way of how you are running your, like what's your driver application. So with Spark, although like for us, we are not going through this because we are using Java, but if you're using Scala or you're using Python, then there is a shell, like you can utilize Spark shell. So with the Spark shell is going to be your driver application. So it's considered as like you are gonna run commands on a Spark shell, and then you tell it, okay, load file, do this, run this script, run this file, and so forth. So if you're utilizing Spark shell, or when you're using PySpark, or when you're using Scala, so you can like make use of the client, your Spark shell client as your driver application. But in our case, we are running Java. So what we do is, after creating the application, you can submit your job to your cluster. This is in the case if you have a cluster, that is. But like for us, we are doing the standalone, so we don't build our own cluster. But nevertheless, if you have your own cluster, then with Java, you need to submit your job for execution. So there is no client. The client is going to be the driver running on the cluster. Also, like this is the case in terms of if we're talking, let's say, industrial applications. Like the issue with running with Spark Shell or like when you're using Python or Scala, if you're using the shell, then the driver application is going to be the shell itself. So let's say for any purpose there is a network disruption, then the driver will be cut off the cluster, and hence that can create a problem. Like if you submitted the job using the Spark Shell and then you turned off your machine, then the job will terminate. That's why in industry, like with industrial applications, they don't do this. They don't, like for testing purposes, they use the shell because it's faster to, like, say, load the file, do this, do that. But once you have your job and you want to submit it to the cluster, you submit a job through the submit script so that the client would be residing on the cluster. So you can submit the job and turn off your computer and go home. There is no problem with this because the client is going to be on the cluster side and the driver is going to be, on the cluster side, and hence there is no problem if your original client is disrupted. So Spark Submit, that's why it's very important, because otherwise, like, you cannot rely, even if you are using the Spark Shell, it's not recommended for industrial purposes if you submit the job on a machine and then leave and go. So with our example, first thing what we have done in the activity is creating our RDD, so loading the file from disk. If it is local disk or if it is HDFS, then you load it into a Java RDD. And in this sense, if it is a text file, so it's an RDD of strings. And then you start with the transformation. So what you are going to apply on this RDD. So first thing, do flat map. So tokenize all the words. Create a huge list of all the words. And then map to pair, create pairs of each of the words with hard-coded, and then reduce and so forth. So, and the final result here, which is the action, like the final step, the action is save to disks, the count and save to disk. So this is the final aggregation function, the action. I'm saying do the count and save to disk. So this is going to trigger the transformation and write the results on local or HDFS file. So when we look at it from a Spark application perspective, from cluster perspective, so this is your application, your driver application. So in that sense, if it is you're submitting the job, so the driver is going to be on the cluster side. If you're using Spark Shell, then the driver is going to be on your PC side. So you need to pay attention to this. And then creating the jobs, like once you have, like you submitted your driver application, Spark determines like what's my plan, what's my execution plan, what's gonna happen, and then the cluster manager is gonna start with segregating the task according to the stages of the plan into worker nodes, and then for each node there is a Spark executor that take one task and perform it, and then the results can be written back to HDFS or Amazon S3 or so forth. So in that sense, this is how it's gonna be happening in your Spark cluster perspective. Like the cluster manager can be like local, if it is Spark native, like you're using Spark as the cluster manager, then it is more local threads. Or you can use Mesos or Yarn for this. So you can rely on Mesos or Yarn to do the management of resources for you. Like with industry, you'll see that Yarn is very popular in that regard because most of the time it is also utilizing like the power of Hadoop. If someone, like if within the organization they need to use other tools, so they prefer that, okay, you utilize HDFS and Yarn because that's already taking care of other jobs from the Hadoop ecosystem. So rather than you recreate anything, or like you use Mesos and have your own cluster, you make use of Yarn, which is already catering other jobs. And also when you're using this, you're also making use of the security features for Hadoop. Because as I mentioned in the last lecture, Spark has some security features, so it is utilizing RPC authentication. So it has some of security functionalities, and it has its encryption. So if you're running it standalone, you can still get some level of security, but it is not as mature as what Hadoop security is now. Because on that level with Hadoop security, you have node storage encryption, you have transfer encryption, read and write for the storage. Also, it is encrypted on that level. And even Yarn, you can specify the policy that allows specific users to utilize some resources in according to others and so forth. So the security within Hadoop is also much mature. So that's why even that make the option of using Yarn as the cluster manager as an attractive option in industry. Once you have your application and say, okay, now I want to submit a program to the cluster, so you need to utilize the Spark submit script. So you specify like within your, in that regard here, your application, your jar, if you're bundling it as a jar file or as a Java application, then you submit to Spark using Spark submit. And then you can also determine like, okay, here you determine what's the, like the details of how the cluster should manage your application. So should it utilize Yarn? Should it utilize, like, is it locally run on the machine? And so forth. Like even sometimes if you're utilizing Yarn, you can specify that, okay, for this purpose, I don't want it to run on Yarn. I want to run it only on local. So that's like, doesn't make it implied within your cluster that if Yarn is being used, if within the Spark submit, you don't specify these details, then it's not gonna utilize Yarn. It's not gonna, like let's say in the web presentation, it's not gonna display the name of the application. That's why it's important that you include such details in order to utilize whatever you want to use as a cluster manager or display the name of your application or so forth. In terms of if, because here we're saying you're gonna submit to the Spark, like you submit the Spark job to the cluster. So if within your application, you can also stop like you put a condition that can stop your job from executing using Spark context stop. So in that sense, if you say, okay, if let's say the memory utilization is more than this, or disk utilization is more than that, or if I get more result in this regard. So you can set up a condition, like even if it is error catch condition, you can say if this happened, then stop that job, like terminate that job so that everything is like stops and you don't like fill up your storage with garbage and affect other applications and so forth. So there is also a possibility to stop the job from executing. So when we're talking Spark submit, these are the most common parameters you need to cater for in order to specify your job. So you need to specify what's the manager, like what's the cluster manager that you're gonna utilize within the master parameter. You need to here also specify what's the class of your application. So if you're executing the main class, you say if you're creating another class, if you named your application with a specific class, you need to specify the name of that class. And then you can even specify the memory to, such as for each executor, I wanted to utilize this much of memory. So this is like when we're talking industrial application, you need to think of, okay, maybe within this cluster, it's not only me running all the Spark jobs. So you need to evaluate, okay, in terms of priority, should I preserve more, should I block more resources, or should I stay like, okay, it's not urgent, so I'm gonna just specify 2 gigabytes of memory I need to block for these resources and so forth. So like as an example, here you say Spark submit. The master is, I have a Spark cluster, so I provide the URL for the Spark cluster. And then the class that I want to run is like word count. And then the executor is, I'm saying, okay, the executor memory should be 2 gigabytes. And you can put other options like here, if I want to add another, like I want to load another jar of file, like dependencies, what we have in terms of Spark. But in general, like depending on, like if there are other libraries you're calling, then you need to include it here in your application and say, okay, what are the things that I want to load in order to execute my application? So this is like roughly once you're submitting your job using Spark Submit. These things like the common, there are other options. Definitely you can have a look at it from the documentation perspective, but these are the most common ones, specifying like what's the cluster manager, what's the name of my application, the Java class name, and then like what's even like here the name parameter. This is more for presentation purposes, like when you're illustrating your web interface for Spark, because like when we're talking Spark cluster, you can also access the web interface for monitoring the Spark tasks, like the jobs that you have submitted, and even like what we talked about in regard to what's the execution plan, what's the DAG. You can also visualize these on the web interface for Spark within your Spark cluster. So the name here can be like for the name that it's going to be illustrated in the, your web UI, the web interface that you're going to utilize. So just like a human readable so word count, so that whoever opened that URL, they can see what is this job is being submitted. So this is what's the web UI can look like. So here you can see, okay, for like the default URL, if you're using local, you can access it with port 4040. Pay attention that for our case, it's not going to be accessible because we're not running a cluster. But if you are running your own standalone cluster, then you're going to be able to access this. And then the details of that job, you can go into for each part and see, okay, show me the execution plan. So by clicking at the information, and the details can show you what are the stages and how they were executed. So this is also a very helpful tool, so that if your application, you want to see how many stages there are, and then maybe, okay, revise, I can see, oh, I have too many stages, that means I'm writing too many times in memory. I should just try to bundle these transformations together. Maybe I redesign my solution to make better performance. So the web console can help with having this overview of your application, how it's being executed in Spark as well. Any questions? So for our second assignment, it's going to be about Spark. So what we are going to do to have some problem, which is graph-related problem. So we are gonna ask you to solve it using Spark Core. So don't think that because it's graph related, you need to use graph X, which is another component of Spark. No, we want to use Spark Core in order to resolve, like start weighting your graph presentation. So we're gonna release it's currently under review, so hopefully either Friday or Monday we're gonna release the specification. It's gonna be due in 2 weeks, and the weight for it is 25% of the total mark. So it's heavier than the first one. So try to do things. And just like iterating in regard to the final exam, it is now 40% of the overall mark. So just like what I mentioned last time. Yep. Sorry? No. So last year it was, I asked them to remove it. I hope that they did. Okay. So concentrate, because like for me, I weight assignments more than final exam. That's why I want that you make use of the practical experience. Final exam is going to be a mix, but nevertheless, it's not going to be like a project. So the experience with the project is more valuable for me. Any other question? Okay, if there is no other questions, then thank you for attending and see you Thursday.
Still cannot understand this.
Just a second.
We can treat this partition as one worker, right? This partition is a one
Yep.
worker.
So one is a partition. So this only one is a partition.
Yes, this only
So
one.
the whole thing is a data frame. An RDD.
Yeah.
The RDD is partitioned into small partitions.
Yes.
And like when you apply flat map on this partition, you're gonna get this partition. When you apply map for this partition, you're gonna get this partition. These whole top three, the top ones,
Yeah.
they can be a single task that run on a single machine.
Yes. And what I cannot understand is this. Where is this partition located in?
Okay. So this can be on a different machine or the same machine. It's now like free for all because the results of the last map here is going to be persisting in memory. And this is the memory of the shared memory of everyone. Like because we're talking cluster computing.
This part of memory is its own memory.
Yeah,
Single nodes.
Single nodes, but we're talking clusters, so it is shared memory between the cluster nodes.
Yes.
That's why we call it a cluster, because like here it's more like our own shared memory.
Oh.
So it's not gonna. Yeah, the one managing that is the cluster manager, but like this one machine can access the memory of another machine.
Yes.
So there is no problem. That's why it's a cluster in the first place.
Yeah.
It's going to be through a network, definitely, but nevertheless, from the perspective of the node, it's our own memory.
Yeah.
There is a mechanism like in the action like the mechanism in the transformation, like different tasks.
Sorry, the transformation, what?
Like if we do we need to separate the job in action?
No. So for you, like what I'm talking about here in terms of narrow and wide and stages, this is not your job. For optimization purposes, like if let's say you have, like you submitted your the job, and it is like the results, the end result is gonna give you correctly that this is the number of words, this is counted this much. So the output is correct, but you look at how many stages do you have in your job, and you find like, okay, for a simple job, you're having 5 stages. This from optimization perspective is not very good, because what does that mean if you have 5 stages and it is a simple job? That means your 5 times your persisting data in memory, and hence like you're wasting a lots of memory. If it is a complicated job and it requires this, there's no problem. Like it's not like no, we should never do this. No, sometimes if you have lots of transformations, that's perfectly fine. But if you have like 5 transformation in total, you have 5 stages, then there is something wrong. They are not doing things properly. So you need to think about redesigning your application. But it's still, the application is gonna run and it's gonna give you the right results. But from optimization perspective, it's not optimum. So that's the only thing. Like, but from execution, it's gonna give you the right result. And Spark in the back, like under the hood, is gonna manage all this. So Spark is not gonna complain. But if you compare your job versus an optimized job, your job can take like, let's say, 10 minutes or more. Let's say 10 minutes, or while optimized job can take 1 minute. So it's gonna affect performance if you are writing to the memory many times.
And in this instance, is it necessary to persist this RDD?
No.
No.
There is, like, in this example, absolutely do not persist anything. Because here, there is like, these transformations are one after the other. The only instance of persisting is because here the reduce by key requires data from multiple jobs. So this is like why you need it. But do not manually do persist for this case, because it's absolutely unnecessary.
Yeah.
In here, the
This
Spark
step.
persist is the you do it.
Yeah, it will do it automatically. Yeah. This, like, even if you do very bad job in how you design your application, Spark is gonna manage it.
Okay.
So it's gonna say, okay, I don't care. It's gonna be like 10 stages, I don't care.
Yeah.
So it's gonna manage it by itself. You don't need to do anything, but the performance is gonna be bad in comparison if you design it properly.
Okay. So I want to make sure that this one, my machine would, when I run my program, my machine would set 2 different paths.
No,
One
not
is
necessarily
the-
2 different paths. So if you're relying on a cluster manager, then this path.
Okay.
If you're not relying on a cluster manager, then there is not going to be manage of resources. It's going to be more like all the jobs are going to be, like, this is more on a single machine. So this
So
is
is
like,
that, so if I use this one, is I set master as local.
yeah, exactly.
Okay. So if I use, for example, the Mesos, I set master.
Exactly, Mesos, exactly.
Oh.
So Mesos is going to be the one managing your resources, or Yarn is going to be the one managing your
Okay.
resources. Or for standalone, it's going to be Spark
one.
scheduler is going, it's going to be one, but Spark is going to manage it as well.
Okay.
So I can only choose one of them.
Yes.
Okay.
Can I
So
choose both
because-
of them?
No. No, because like it doesn't, if you have Yarn, then definitely use Yarn.
Okay.
So that's not because like it's gonna be managing resources for you. Here it's like it's bad performance in general because like you're not gonna be. So that's why I said if it is a local machine and you're just doing for testing, then it makes sense because you don't have resources to manage in the first place. But if you have like if it is 10 computers, then you need someone to do that for you.
So if I not this part, so if I just say set master local and without anything else, is I just have 1 worker.
One worker.
But if I have local and brackets and 5, I would use my local machine, but I would say
5 workers in your local machine.
Okay.
It doesn't make sense in the real world scenario,
Okay.
but
Yeah.
if for testing purposes, because if you know that for me in my company we have 5 workers, so I will do this, then you can do it for testing purposes.
Okay.
It doesn't make sense in the real world scenario.
And this work and these workers will work parallelly or
Yes, parallelly. So even if it is on your own machine, they work parallelly. But like they are consuming the same resources, so performance-wise, you're not going to get anything.